Hello friends, welcome to the session, continuation of chapter 4, that is inverters. In the last session I discussed about what exactly current source inverter, and I given for purely resistive load and purely capacitive load what are the waveforms that I given. But I told that in current source inverter there exists a forced commutated current source inverter and load commutated current source inverters also. If the power factor is lagging, then we can use forced commutated current source inverter. If the power factor is leading, then we can use load commutated current source inverter. Even if the load power factor is unity, we are using the forced commutated current source inverter. Okay. Now, here in this section, I am explaining what exactly a capacitor commutated current source inverter with respect to R load. Capacitor commutated current source inverter this is one of the example of forced commutated current source inverter. In current source inverter, once we are using forced commutation means it must consist of one capacitor. Then only forced commutation is exist. Okay, that means a capacitor commutated current source inverter this is one of the forced commutated current source inverter. It is a forced commutated current source inverter. It is forced commutated CSI. It is one of the forced commutated CSI, current source inverter. Okay. Now, first I will draw the circuit. What exactly forced commutated circuit for CSI. Then later on we go for what is the waveforms and what is the analysis. Okay. So this is the circuit we are using for forced commutated CSI. Current source inverter means input is constant current source. Let this is I. This T1 thyristor. Once we are talking about commutation means the devices must be thyristors. The switches we are using is the thyristor, that's why we are using the commutation circuit. Where capacitor is the commutating element. Where R is the load parameter. So the voltage across the load is V0. The current through the load is I0. Current through the capacitor is IC. Okay. This is T1, this is T3, this is T4, this is T2. And this current is I. This is IC. Okay. This is the circuit we are using for forced commutated current source inverter. Let's assume that with this assumption only we are explaining this concept. Let's assume that the initial voltage across the capacitor is minus plus V1. The initial voltage across the capacitor is minus plus V1. We can operate this circuit in such a way that we want to convert. You can operate this circuit in such a way that we want to convert constant DC to AC. We want to convert DC current to AC current. Actually, let's assume that this is the assumed current direction. This is the assumed current direction. Okay, assumed load current direction. This is actually this load current is I0. Okay, this is I. Then we can switch on this circuit in such a way that, for example, for 0 less than or equal to T less than or equal to T by 2. We can turn on T1, T2 is on. Here no need to draw the equivalent circuits, all this directly I am giving. T1, T2 is on. Then tell me, if T1, T2 is on, this is the current flowing. There existed two currents, no doubt at all, but I am talking about concentrating on load current. If T1, T2 is on, like this current is flowing. This is the load current direction. That this is the current I naught is, this I is same that of assumed current direction of load current na. This is assumed load current I naught. Then whatever the I is flowing is also same direction. That's why if T1, T2 is on, I1 equal to plus I naught. Sorry, I naught equal to, you take plus I. Because the current flowing is same that of the assumed direction. Okay, we are assuming load current and T1, T2 is also supplying in the same direction. That's why you take I naught equal to plus I. If T1, T2 is on, we are getting I naught equal to plus I. Now, during this operation, in this capacitor is changing its polarity. Then capacitor is charging, capacitor is changing polarity. The capacitor is changing polarity from minus V1 to plus V1. The point to remember here, the voltage across the capacitor equal to voltage across the load. But you can take this voltage across the load equal to voltage across the. That means if the capacitor voltage is changing from minus V1 to plus V1 means the load voltage is also changing from minus V1 to plus V1. Load voltage is also changing from minus V1 to plus V1. Understood? Okay. This is observation if T1, T2 is on. Now see, for T by 2 less than or equal to T, less than or equal to T. Now what I do means T3, T4 is on. T3, T4 is on. That means when T1, T2 is on, when T1, T2 is on, then the capacitor changing its polarity. This is plus, this is minus. Now, in order to turn off this T1, T2, now what I can do means I will trigger T3, T4. Whenever T3, T4 is triggered, T3, T4 is triggered, then this positive is connected here. This negative is connected here. Then T1, T2 will be turned off because of polarity of capacitor. That means T3, T4 is on because of polarity of capacitor. Because of polarity of capacitor. Because of polarity of capacitor. See, I am triggered this T3, T4 now. Whenever T3, T4 is triggered, then this capacitor polarity is connected here. This capacitor polarity is connected here. This negative with respect to T2, it is under reverse because negative is connected to anode of T2. Positive is connected to cathode of T1. That's why T1, T2 will be turned off. Because of polarity of capacitor, T1, T2 is turned off. T1, T2 is off. Now, if the T3, T4 is conducting, see the direction of current. If T3, T4 is conducting, this is the load current direction. Assumed load current is this one. This is assumed load current. But T3, T4 is conducting in the opposite direction of load current direction. That's why you take it I naught equal to minus I. Then what about capacitor? Capacitor polarity changing from plus V1 to minus V1. Because now this polarity changing again. T3, T4 is conducting now. If T3, T4 is conducting means this polarity is changing from plus V1 to minus V1. Then it becomes plus, again it becomes minus. Initially minus plus. This is the initial polarity. If T1, T2 is conducting, it becomes plus minus V1. Because of this polarity, what about T1, T2 is turned off. If you trigger T3, T4. Then if T3, T4 is conducting, again it is changing from minus to plus V1. Again we are getting initial position. Then cycle will be repeated. Understood? This I naught equal to minus I. Then capacitor is changing its polarity from plus V1 to minus V1. Again T1, T2 is triggered. Then T3, T4 will be turned off. Now this capacitor polarity becomes minus plus. If T1, T2 is triggered, plus is connected here, minus is connected here, then T3, T4 will be turned off. Like this circuit operates. That's why by using this capacitor, we are commutating the thyristors. Yes, sir. We are commutating the thyristor. Now, based on this knowledge, now you can draw the waveforms. What are the waveforms we are getting? That you concentrate. Yes, that you concentrate all these waveforms. This V naught, I naught, VC waveforms are same. This V naught, I naught, VC waveforms are same. Or if you take this is V naught and VC waveform, then I want to draw the I naught waveform. This I naught, concentrate on I naught waveform. Then you can draw the IC waveform. This is IC. Then you can draw the voltage across T1, T2 waveform. Voltage across T1, T2 waveform. Okay. Now if you trigger, now this V0, VC, both are same. The capacitor voltage is changing from minus V1 to plus V1. Okay, minus V1 to plus V1 it is changing. The capacitor voltage is changing from minus V1 to plus V1. Understood? Okay. Then if you take for IZ1 and IZ2, if T1, T2 and T3, T4 is triggered. If triggering pulse is considered. This is T, this is also T, and this also consider T, this also T. First, parallelly, all of you draw this form, parallelly draw the waveforms. Yes. Let this is A, this is B. Okay. If I am drawing this waveform is IAB waveform. Let this is IAB I am drawing. Later on I will draw this. This IAB. If T1, T2 is conducting, we get plus I. If T3, T4 is conducting, we can get minus I. Again T1, T2 is conducting, plus I. Again we are getting minus I. It's correct. So, okay. What are the wave shapes we are getting? Here T1, T2 is conducting. Here T3, T4 is conducting. Again T1, T2 is conducting. This is T by 2. This is T. Okay. Okay. Now we can draw the voltage across the load waveform. This is IAB waveform now. T1, T2 is conducting, current is this direction, A to B. T3, T4 is conducting, B to A. That's why I take a negative. Here I am drawing, this is T and this is also T. Here I am drawing the V0 or VC waveform. If you take V0 or VC waveform means the voltage across the capacitor is changing like this. Okay, it is charging from minus V1 to plus V1. Again it is charging from plus V1 to minus V1. Again it is charging from minus V1 to plus V1. This is capacitor voltage. Minus V1 to plus V1. Again plus V1 to minus V1. But point to remember, this is also equal to I0 because it is a resistive load now. Voltage and current waveforms are same. If you take in terms of current means minus I1 to plus I1. Then plus I1 to minus I1. This is minus V1 comma minus I1. Like this may be also equal to I0 because in RC circuit, it's RC parallel circuit now, how this current is changing, I0. Minus I1 to plus I1, then plus I1 to minus I1. Like that it is changing. Okay, that is the V0, VC and I0 waveforms are same. Now I am drawing the, okay, see, how to change the current, IC current. Current through the capacitor. Current through the capacitor. The current through the capacitor is, you can get like this. We are getting like this, where IC equal to I minus I0. Can I accept this? What is I equal to? I equal to IC plus I0. Then what is IC equal to? I minus I0. This is IC plus I0. IC equal to I minus I0. This waveform I am drawing. IC current waveform. Then this IC current waveform we can get like this. RC circuit, it is exponential current. Exponentially decreasing. get the like this. This is IC current waveform. RC circuit current na exponentially. This is capacitor is charging. The current through the capacitor is exponentially decreasing. Capacitor is discharging. The current through the capacitor is increasing. The current through the capacitor is increasing. Understood? Then again decreasing. Like this we can get. This is IC current. Then you draw the V in waveform also. Any waveform we can draw. I am drawing this V in waveform also with respect to input voltage. Then with respect to input voltage means then this output voltage is equal to input voltage. But we can get like this. Just like what I explained purely capacitive load also. We know this one cycle of output, thus with respect to input it must be 2 cycles. Yes, this is V in waveform. Then I want to draw the voltage across T1, T2. Voltage across T1, T2. VT1 and T2 waveform, right? Here T1, T2 is on state. If T1, T2 is on state, tell me, voltage across T1, T2 equal to 0. Here T3, T4 is triggered. If T3, T4 is triggered, suddenly the T1, T2 is reverse bias. Then if T3, T4 is, if the capacitor is changing its polarity, the voltage across T1, T2 is also changing. The voltage across T1, T2 is also changing. Here T1, T2 is conducting. Okay. Then this is about what waveform? V in waveform. You get like this. This time is the time the voltage appear across the time taken reverse voltage is equal to circuit turn off time Tc. Okay. Like this we can get the different wave shapes. This is T by 2, this is T. This is T by 2, this is T. This is T by 2, this one is T. This is T by 2, this one is T. Okay, these are the different wave shapes we are getting in capacitor commutated current source inverter. This is IAB, this is V0, VC and I0 is also same. If the voltage is changing from minus V0 to V1 means then I am assuming that current is also changing from minus I1 to plus I1 because of initial voltage. Assume that the initial voltage is minus plus V1, that I told already. Then we can get like this. Now based on this we want to do some analysis that is important for commutative point of view. Okay. So okay, understand? Okay. Now down this. Quick. The point, it is not exactly triangular. This is exponential. That point to concentrate. It's not triangular waveform. This we get. Okay. Now we want to do some analysis here. Because of RC circuit, the current changing is like this. Exponential voltage is exponential, current is decreasing. So some analysis here. Do the analysis. This analysis of capacitor commutated CSI. Listen please. We know from the circuit what is I naught equal to or I equal to I naught plus IC. From this you know. Then what is I naught equal to I minus IC. I naught equal to I minus IC. Now from this I want IC equal to I minus I naught. But I want maximum value of I naught, maximum value of IC at t equal to 0. This is the instant at t equal to 0. Okay. What is I naught, you tell me? At t equal to 0, what is I naught minus I1? This is V naught, Vc, I naught waveforms are same. Then what is I naught equal to minus I1? You substitute here. What is IC equal to I plus I1? But this I plus I1 is maximum value. This is this current equal to I plus I1. At t equal 0, this IC current equal to I plus I1. This I plus I1 is not constant, exponentially decreasing. That's why we can write like this now. Therefore, where IC equal to I plus I1 into, you consider exponential component also. That is e power minus 1 by RC into t. Okay, this you substitute here. Then what is I naught, you tell me? I naught equal to I minus I plus I1 into e power minus 1 by RC into t. Okay, now you can take then I naught equal to take I is common 1 minus e power minus 1 by RC into t plus I1 into e power minus 1 by RC into t. Okay, let this is equation 1. Understood? Tell me, at t equal to t by 2, at t equal to t by 2, what is I naught equal to? I naught equal to I1. Accept this. At t equal to t by 2, current is changing from minus I1 to plus I1 because voltage across the load is changing from minus V1 to plus V1. That's why taken as it is changing from minus I1 to plus I1. Understood? At t equal t by 2, what is I naught? I naught equal to plus I1. Then I naught equal to plus I1. Then you substitute here I1 equal to I into 1 minus what is t equal to t by 2? 1 minus e power minus t by 2 RC plus I1 into then what you can get? E power minus t by 2 RC because t equal to t by 2. Then you bring this side. Then what you can get? This is minus, this is minus. Plus into minus, minus. This is also minus. Okay. Then you bring this side. Then what you can take? Take I1 is common. I1 equal to I1 into 1 plus e power minus t by 2 RC. E power minus t by 2 RC is equal to, then what you get? I into 1 minus e power minus t by 2 RC. Then what is the expression for I1? The expression for I1 equal to, then what you get? I into 1 minus e power minus t by 2 RC by 1 plus e power minus t by 2 RC. Okay. This is the expression for I1. Let this is equation 2. Okay. Now substitute okay, equation 2 in equation 1. equation to follow all of you parallel, you note down, follow this quick, concentrate. Here I want to make some final observation, that's why I am doing all this analysis. Okay, now tell me. Then substitute in equation 1 means what is I naught equal to? I naught equal to I into 1 minus e power minus 1 by RC into T minus what is I1? I into 1 minus e power minus T by 2 RC by 1 plus e power minus T by 2 RC into e power minus T by RC. This we can write. Now by simplifying this one, we can get I naught equal to, then I naught equal to I into 1 minus 2 into this, by simplifying this one, directly I am writing, then by simplifying this one, I naught equal to I into 1 minus 2 into e power minus T by RC by 1 plus e power minus T by 2 RC. This is the expression for load current in a RC circuit. In a capacitor commutated current source inverter, what is the expression for load current? I naught equal to I into 1 minus 2 into e power minus T by 2 RC into 1 plus e power minus T by 2 RC. Understand this? But I want to find out what the expression for load. Let this is the equation 3. Now I want to find out what is the expression for load voltage. Then how to find the expression for load voltage? Okay, is it completed? Okay. Then you tell me what is the expression for load voltage. Then you want to find V naught equal to, that you can get I naught into R. Then load output voltage equal to V naught equal to I naught into R. Then V naught equal to I naught into R means IR into 1 minus 2 into e power minus T by RC by 1 plus e power minus T by 2 RC. This is the output voltage. Quick note down. A current source inverter. That is a calculation of, that you concentrate calculation of circuit turn off time. Okay. Calculation of TC. Calculation of TC. The point to remember, if at T equal to TC, the voltage falls to 0, V naught falls to 0. At the time of T equal to TC, the voltage falls to 0. This V naught equal to 0. That means apply that condition. At T equal to TC, V naught equal to 0. Then if you apply this, what you can get? 1 minus 2 into e power minus T by RC by 1 plus e power minus T by 2 RC. Now from this, what you can get? Tell me. If you can equate to 0 this one, this is equal to 0. Then what you get? S 1 plus e power minus T by 2 RC is equal to, that is 2 into e power minus T by RC. Then what is e power minus t by RC equal to 1 plus e power minus t by 2 RC by 2. Take natural logarithm on both sides. Then what we can get? Minus t by RC equal to ln of 1 plus e power minus t by 2 RC by 2. Taking natural logarithm. Then what is t by RC equal to? This negative sign we can send this side. Then it becomes 2 by 1 plus e power minus 2 by 2 RC. Then what is t equal to? This time is called circuit turn off time. RC into ln of 2 by 1 plus e power minus 2 by 2 RC. Okay, this is the circuit turn off time of capacitor commutated current source inverter. RC into ln of 2 by 1 plus e power minus t by 2 RC. Whatever the load voltage is there, that same load voltage will appear across the input voltage also. That's why you want to calculate input voltage, average input voltage Vin equal to this. You want to find average value of this one means for in one cycle we are getting the 2 cycles of output. In one time period we are getting 2 cycles of output. Then what is the time period? 1 by t by 2 integral 0 to t by 2 V naught dt. Understand? Okay. Then 1 by t by 2 integral 0 to t by 2 V naught dt. Then what is Vin equal to? Average input voltage equal to 1 by t by 2 integral 0 to t by 2. What is V naught, you tell me? This we can. IR into 1 minus 2 into e power minus t by RC by 1 plus e power minus t by 2 RC dt. Then integrate and substitute the limits. Then we can get Vin equal to, that is IR into Vin equal to IR into, then what you get? 1 minus 4 RC by T into 1 minus e power minus T by 2 RC by 1 plus e power minus T by 2 RC. This expression for Vn. By integrating and substituting limits, we can get this one. That you try. Let's note down. Okay, this about input voltage, output voltage expression of forced commutated current source inverter. This final summary I want to give here. Some summary formulas here. Is completed. Okay. This final summary here. Yes. What is in a capacitor commutated current source inverter? Capacitor commutated current source inverter for R load. We are connecting for R load. The expression for I naught equal to 1 minus I into 1 minus 2 into e power minus t by RC by 1 plus e power minus t by 2 RC. This one expression. Then average load voltage V naught equal to I naught into R. Then what you can get, I naught into R, this IR into same equation 1 minus 2 into e power minus t by RC by 1 plus e power minus t by 2 RC. This is one expression. Then you tell me, what is the circuit turn-off time? The circuit turn-off time Tc equal to RC into ln of 2 by 1 plus e power minus t by 2 RC. Next, fourth one. What is the input? Average input voltage equal to IR into average input voltage. IR into 1 minus 4 RC by T into 1 plus 1 minus e power minus t by 2 RC by 1 plus e power minus t by 2 RC. This is the average input. These formulas mainly concentrate. Based on this, we can make some design considerations. If Vin is positive, then Vin into I is positive. Vin into I is positive. Then power is delivered. Source to load. If the average Vn is negative, then Vin into current is negative. Then power is delivered. Load to source. Then used for regenerative application. Used for regenerative application. Like this, we can calculate average input voltage. For example, one observation here, in this circuit turn-off time, take from relation 3. In this circuit turn-off time, if T is increases, if T is reduces means frequency of operation is increases. If T is reduces means TC is also reduces. If TC is also reduces means if T is reduces, frequency of operation is increases. But TC is also reduces. Circuit turn-off time is also reduces. Then if T is reduces means frequency of operation is increased. But the point to remember here, if T is reduces, frequency is increases, that is advantageous. TC is reduces, that is also advantage. But we don't reduce the TC for very small value. Always for reliable turn-off of any thyristor, we can maintain circuit turn-off time is greater than the device turn-off time. That's why reducing T is very small value is not acceptable. If you want to reduce very small value in order to operate at high frequency means, but TC is also reduces. Once the TC is reducing, from this equation I am telling that if TC is reducing, then there is a possibility of commutation failure of thyristor. That's why we cannot reduce. That's why the upper frequency operation of this inverter is limited by TC. The upper frequency operation of this inverter is limited by TC. That one point you remember. The another observation, if T is increases, no doubt at all, frequency of operation is reduces. If T is increases, frequency of operation is reduces. Then whatever the wave shape we are getting, output current or output voltage wave shape we are getting, then the shape of that waveform nearly becomes flat, the shape of that waveform nearly becomes square waveform. Nearly becomes a square waveform. That's why the lower frequency of operation of this inverter is limited by shape of the waveform. Limited by shape of the waveform. Then during the operation of this inverter circuit, if you want to get pure square waveform, if you want to get pure sinusoidal waveform, and if you want to operate at high frequency, then which design considerations are required? That is very important practically. That is a practical consideration. What I am telling that if T is increases, circuit, if T is reduces, frequency of operation is increases. That's why the upper frequency operation of this inverter is limited by which one? Circuit turn off time. We cannot reduce very small value for circuit turn off time. Then the lower frequency of operation, this inverter is limited by shape of the waveform. Then during the operation of this inverter circuit, then to get the pure square waveform, or if you want to get the pure sinusoidal waveform, what is the design considerations we can use? How to design this capacitance value? How to make the switching frequency? How to make the switching frequency of these thyristors? All these I want to discuss. That is the practical design consideration of inverter. That is the capacitor commutated current source inverter. Okay. In the next session, I will continue with what is the design considerations in the case of capacitor commutated current source inverter. Then I want to discuss there is another one current source inverter is there, that is ASCII, auto sequential commutated inverter. Then I will discuss some points, 1 or 2 points with respect to 3-phase current source inverter. With that, current source inverter concept will be completed. Okay, what is the design consideration of this capacitor commutated current source inverter in order to get the pure square waveform, in order to get the pure sinusoidal waveform, that I want to discuss. After that, there is another current source inverter is there, ASCII, auto sequential current commutated current source, auto sequential commutated current source inverter. Then I will give 1 or 2 points with respect to 3-phase current source inverter. I already discussed 3-phase voltage source inverter. Okay, but here I want to discuss 3-phase current source inverter with respect to that. Then later on we go for another concept also. Okay, understand? So okay, that points you concentrate. Mainly this formula is important based on this one. Still now in GATE exam based on this concept, still now no question from 1991 to 2018, no questions from this concept. But in future we may expect. That's why I am giving this analysis. But if the question is asking based on this concept, means compulsory we can expect only from the circuit turn off time. That you concentrate. Understand? Okay. Thank you. Okay, note down. If anybody not note down these points, then note down. In next class I will continue. Thank you.